All right, let's get rolling. So first up then, we have Sam Findlay from Wollongong, who's going to, what should we say, convene a communication conversation with Dr. Cathal O'Connell. Sam, over to you.
Thank you. All right, so that should be up now. So I'm going to do something a little bit different, I should say, to what I was originally going to do. I was going to come up here, give a bit of a quick session on science, communication, focusing on LinkedIn, building on my presentation last year. But instead, I've decided to have a conversation with Cathal, who most of you in here should know, most of you online should know as well. Before I get to Cathal, I'll just go through a quick number of slides, introduce myself for those online, or those of you who don't know me, you probably should if you're here. If you don't know, that's me. This is me. Sam is my name. Yeah, one too many faces. You might have a third online. So I'm one of the communications and media officers here. I work closely with Lauren. I'm more on the sort of social media side of things, website. Write a lot of stories here, interview you guys from time to time. So you can follow me on LinkedIn and Twitter if you want. Bit of a plug there. Now I'll introduce Cathal. He's coming back. For those who don't know Cathal, he's an ACES associate investigator. He's also a BC postdoctoral fellow at RMIT. He's also on LinkedIn and Twitter as well, so you can follow him. Cathal and I also had a conversation on the ACES podcast last year. There's a QR code there, so feel free to take a photo of that if you'd like to bookmark it and save it for later. And we talk a lot about science communication on that podcast as well. So what we're going to be talking about today in this 15-minute time slot builds on a lot of what we talk about in the podcast. So feel free to go and listen to that as well. So I'm going to stop sharing. And then Cathal and I can begin our conversation. So first of all, Cathal, do you want to just give yourself, I've done a quick introduction, but do you want to just give yourself a more in-depth introduction about your background, and I guess what we're going to be focusing on a little bit more is your background in science communication as a science writer.
When I finished my PhD, I actually couldn't find a postdoc for a while, so I looked into science communication as a profession. I was doing some freelance writing, and I was working as a science communicator at La Trobe University. And it was there that I had a break when Elizabeth Finkel came to give a talk. She is the editor of Cosmos magazine. And so I went up to talk to her at the end of her talk, and she gave me the opportunity to come in as an intern. So I worked with her and Alan Finkel on their Cosmos magazine for the next few years in a freelance capacity. So that's a bit of my science writing career, I guess.
So did you do a fair bit of science writing while you were studying? I guess your undergraduate degree, master's, and your PhD as well?
Yeah, I mean, I took the opportunities as they came up and entered in a couple of competitions through Natalie Fox. Got to write something for the Illawarra Mercury about PhD life, and building up that little bit of portfolio. That was what I was able to use then to get this internship opportunity. You kind of build up from small opportunities, and then you use those as stepping stones to get the next.
So how did you approach writing these stories as a science writer? With obviously speaking to researchers here who want to get their work noticed, I guess, do you have any advice, from both sides of being a science writer and a researcher, how you would approach writing these stories, and how your research that you write about would get your attention. I know we spoke about before, we were catching up about having this conversation about finding something that the general public can relate to, and having some sort of hook. So I'm wondering if you could just speak about that a little bit.
Yeah, sure. So when I started, I mean, I was making the same mistake that most people do, which is to try and explain everything in about the science, and you just can't do that. You really have to. It's not just a case of simplifying things down or making it entertaining or whatever. You just don't have the scope to explain every idea. So one of the things I learned in the early days is that every article can really only have one new idea that you'll explain, and to get people's attention, you need some kind of a hook. So it depends on your audience. When I was writing for Cosmos, the hooks that I tried to find were links to science fiction, because that was the audience. The audience loved science fiction and any story where there was a relationship to some element of from science fiction, movies or whatever. That's what would go very well. But equally, what can work equally well is any connection to daily life. Anything that you're using in your lab that is also being used in a home environment, that really gets people's attention. And there's been some great stories coming out of ACES in the past where that's been used, such as the Vegemite printing story. That was a great success a few years ago. Even the biopen itself, that's been a huge media success around the world. And I think part of the reason why is because everyone can identify with just writing with a pen, and that's one of the things that allows it to people get the idea straight away. So that's really the key, is to find some kind of hook, some kind of and
Yeah, okay. I'm wary of time, so I'll move on to, I guess, the next sort of topic, and that's the importance of social media. Something that I've spoken to everyone here at IPRI and even at ACES in previous webinars I mentioned at the start. LinkedIn and Twitter specifically. You're on both as well, and you're very active. I know you've got over 800 followers on Twitter, and on LinkedIn you've got quite a few connections as well. Firstly, what do you think of the importance of social media, and how do you utilize it, and why, I guess?
Yeah. Well, I'm not really a very social person, but I use it purely for self-interested reasons, because I know that if, especially Twitter is a good way of communicating results to the academic peers. It's just a way of getting your work out there and generating more readers, more citations. So what we tend to do is, when we have a big paper, we do a tweetorial, which is breaking the main ideas of the paper down into really small little chunks, using imagery and videos to explain it as simply as possible. And that's the kind of thing that can be shared widely. And similarly on LinkedIn, pretty selfish reason to do that is because our research jobs are so precarious these days. You need the bosses of your university to see what you're doing, and they're the kind of people who tend to see this stuff on LinkedIn. So that's one of the reasons why I'm active on LinkedIn, to try and make sure that what we do is visible to the guys who make or break your career, basically.
And you mentioned to me as well, when we were chatting about this before, when we were planning this, about how journals actually check how often their papers are shared on social media, and that helps with ranking and turning up in search engines and various research websites. Is that correct?
Yeah, that's right. So quite a few journals nowadays subscribe to a program called Altmetric, and that will track all of the news articles, all of the tweets, and all of the shares on Facebook about a particular paper. So you can see it on the page of your paper, you'll see this little box there with the metrics in it, and that's something that the editors of these journals are paying attention to, because they want their the journals that they publish to have the biggest exposure. So and then the journal editors themselves will also share the work. So it's just a good way to get in with the editors of the journals themselves.
Okay, well, I'm wary of time. I've only got a couple more minutes, so I don't want to get gonged off. I'm going to skip to the last sort of question I had for you, and that's, where do you think the future for science communication, someone who's been, a science writer, as I mentioned, and as a researcher, what do you think the future is for science and science communication in, say, the next 5 years or so? It's obviously going to become more and more important. I was just wondering about your thoughts.
Yeah, absolutely. So science writing as a profession is on the way out, probably, at least in for newspapers and for the general public. What's happening is it's being put more on the shoulders of the actual scientists to do the communicating. That means writing for the conversation. It means promoting promoting the work on social media. So more that kind of work that's traditionally been done by science writers or journalists will be done by the actual academics themselves. And that's up to everyone else to get involved.
Yeah, great. Well, we're at 15:15 now. We're pretty much bang on our 15-minute time slot, so I don't want to run too far over. So thank you for joining us, Carl. Thanks for the conversation. You're a bit glitchy in and out, but yeah, we got to hear you nonetheless. So yeah, thanks very much. That's yeah, if you've got any questions, I don't know if we're going to take questions now. We probably don't have time, but you can email myself or Cathal, or you can tweet us or send us a message on LinkedIn. Thanks, Carl.
All right, thanks, guys. Thanks, Cathal, for coming on like that, and Sam for organising that. As Sam said, I think we might just press on, send any questions directly to either Sam or Cathal, or Sam will certainly handle any questions you like. In the meantime, then, let's press on to our next speaker, who is Dr. Andrew Nattestad, who's going to talk about the scale-up of reactors for CO2 reduction. There we go. Thanks.
Okay, good afternoon.
Yep.
Yep, so as Doug introduced, I'm going to be talking about scaling up CO2 reduction reactors. This is mostly focused on work that I did last year at UAW and at the very start of this year. So I guess the first thing we need to discuss is why. So there's some very obvious reasons why we want to do CO2 reduction. So that's decreasing the levels of CO2 in the atmosphere. We all know by now. We've heard many introductions talking about the effects of this. The other thing, which isn't always mentioned, but is probably one of the main or most important things that sort of drives us to actually be able to do this at any kind of scale, is that the products of CO2 reduction are actually quite useful as building blocks for chemicals or other fuels. So that's kind of puts a bit of motivation for us to actually get these things going. In terms of my personal connection to this, and this is part of an ACES project, doing this sort of scale up begins the process to start looking at things like the durability of the reactor, the balance of plant issues. So that's all the ancillary equipment that needs to go with beyond just having everything sitting in a beaker. Also with CO2 reduction and some similar chemistries, you actually do get much better performance. So if you look at the best 3 electrode performance for CO2 reduction done in H cells, they're typically quite low, whereas once you switch to something like a gas diffusion electrode reactor, as I'll show in the following slides, the performances are actually better. And I guess also probably the most honest, even if it's a little bit cynical, is that it's a great way to actually, we want to be able to show off the catalysts that have been generated within ACES in a way that is much more tangible. So I guess sort of following on from what Cathal and Sam were talking about, something which is able to be communicated to a broader audience. So we start off our journey, and we know that we're way back here on the road, and we've got our sort of eye on the prize of a marketable product. Unfortunately, that's a little bit optimistic, and the pathway probably looks something more like this rather than our straightforward road. But unfortunately, there's no shortcuts. So this journey for me started with taking an existing reactor design. So here, this has been reported in the literature. You can see that there's a series of plates with gaskets and membranes in between. So the electrodes are all produced on gas diffusion electrodes, so that way you can supply the reactant at a great rate and take away the products. Essentially replicated this out of Perspex. So this gave us the benefit of being able to very easily see what's going on inside the cell in terms of any bubble formation. And what we did see was that, yes, there were a lot of bubbles and that they generated a lot of noise in the electrical response. And we also saw that, as you can see from the top image here, that those bubbles tended to often pool, and when they pooled, you sort of lost active electrode area and the performances dropped off. So a little bit of playing around with this, a little bit of tweaking, trying to improve the bubble removal. So in this case, we have the electrolyte flow path going through one of the electrodes such that it should push out all the bubbles out of the way. And we saw there's definitely an improvement. So we were able to get up to at least 3 volts with a relatively smooth and stable current, but still not quite ideal. So a few iterations in between and sort of revised everything to create this reactor, which you can see here on the screen. So one of the key features of this is that all of the inlet and outlet for the reactor are now on the front face, with only the electrical connections coming out the sides, or the top in this case. And you can see, looking side on, basically you have CO2 glancing, making glancing contact with the cathode, cathalite and analyte, which are both cycled through. And then at the anode, you're generating oxygen. So we've got another pathway there for that to be swept out. Now, using this approach, you can see here, this is again the idea of, or the issue of bubble formation blocking up the electrode. So the way that the electrolyte flows in this case actually helps to accommodate that. So you can see that we have electrolyte inlet here. The way that it flows around sort of creates enough turbulence that there's no dead spots, so there's no sharp corners, and the flow actually sweeps everything out as it goes. So it's a lot more successful approach. Putting this to the test under argon and CO2, we saw considerable shift in the onset, and when we took our measurements using the GC, we saw, just using a fairly well reported, so a fairly uncontroversial electrolyte and electrode setup, we were able to achieve around about 50 milliamps per square centimetre at 3 volts. That's a 2 electrode potential, which is kind of on par with the literature, so that's a good start. So here I've just got a bit of a exploded view, so you can see all the different parts. These were all produced on a laser cutter, so they were, the clear plastic plates are made from Perspex. There's Viton rubber gaskets holding it together, and then the metal foils, which are used as current collectors. All the other components are off the shelf, and I did a rough calculation, and excluding machine time and human labor, this type of reactor works out to around about $50, which is pretty good considering that if you want to buy one of or a similar reactor, you probably pay about $2,000 through any of the commercial suppliers. So as I said, one of the important features of this reactor is that all the connections are at the front, and one of the key reasons for that, aside from any kind of aesthetic considerations, is that it allows us to connect up multiple pairs of electrodes in this case, showing in parallel. So we have two cells which we measured independently, and then we connected them together, and we saw that the response was almost exactly as the predicted provides, and then doing similar thing again in series connection. So this is, I guess, a little bit more of an unknown, because when we flow our electrolyte through in the configuration that it is here, the electrolyte actually runs in parallel, even though the electrical connection is in series. So that was kind of a risk that we had to address. And fortunately, we see that the shunt losses are actually not so severe in this type of configuration. This slide summarizes what we've just sort of seen. And so, yes, the performances aren't quite as good as they ideally would be, but they're not so far off. So it kind of feels like there's just a bit more tweaking to do rather than a fundamental limitation. We can also see here that for any of the configurations, we get very similar Faraday efficiencies, and very strongly favouring carbon monoxide rather than hydrogen, which is the desired product in this case, and what we kind of expect using the electrodes that we are using. So the next major issue was looking at scaling up. The way I sort of tackled this initially was just to more or less go direct. So going from a 1 square centimetre circular active area to a 10 square centimetre active area. This didn't perform as well as we'd hoped. And one of the key things that we saw was the need for an additional current collector. So we achieved this using some just metal foils rather than the simple copper tab that we had initially started with. So you can see for the smaller area, whether you go with just a copper tab or a proper metal foil current collector, there's not so much of a difference in the current. But once you start to scale this up, it becomes more and more significant. And here, even with this current collector on the larger area electrode, we're still not getting quite the current densities that we're hoping for. So a little bit more revision on the reactor design. So now we have, as you can see in the bottom right corner here, we have our active area broken up into strips, and in behind that gasket, which you can't quite see from this angle, sit some metal foils, which are used as current collection. And this gives us a little bit higher, quite good Faraday efficiency, so up to about 90% CO, which is great. And brings me to the sort of final thing that we looked at in this study, which was looking at the stability. Unfortunately, the electrodes do degrade a bit over time. There's a number of different reasons which we've sort of identified in terms of sort of contamination and build-up and depletion of certain components. Unfortunately, we haven't quite had the chance to fully investigate this. So this is kind of ongoing work that Claudia will be undertaking, hopefully, if she has time. I don't want to make too many promises on her behalf. But yeah, so again, we can see that there is a degradation in performance. However, if we focus ourselves again on the Faraday coefficient, we can see that that does at least tend to stay relatively stable over at least a 5-hour time course. So this sort of brings us to our conclusions, where we see relatively small losses when we compare our stacked versus individual electrodes. So that's promising. We can further enhance or further decrease the threat from the shunt losses by including a serpentine flow path to sort of physically separate the electrodes a bit more without separating them. We also see that the need for a current collector becomes much greater as we go to larger areas, which is kind of in line with the expectation, which brings us to the further challenges sort of to take us to the next step. So we need to look at even increasing this the bus bar / current collector performance even more, so that realistically just means incorporating a thicker bus bar into the design. We also need to look at going to much larger stacks. So in this case, I've only shown going up to 2 pairs. Realistically, we want to be able to do many pairs, and ideally in series, so we can have a relatively small current flowing through the whole cell, large voltage, so we can minimize our resistive losses. We also want to be able to do stability tests for hundreds to thousands of hours. And I guess then maybe one of the elephants in the room is that we need to actually be able to look at using lower CO2 concentrations. For pretty much everything in research, we use purified CO2. Realistically, that doesn't make any sense from an environmental perspective. We need to be able to use lower purity, such as industrial flue gas, which is somewhere around 10 to 15%. And I guess the ultimate goal is if we can get something which operates even closer to atmospheric levels. And also that we can make sure that in our system, we don't actually release unreacted CO2 at the other side. So with that, I'd like to just thank those involved, particularly Claudia Wagner. And if we've got time for questions, possibly not. But if you've got questions, please feel free to flick them through in the chat or contact me directly.
Thank you, Andrew. That was great. And that's really excellent progress in terms of prototyping towards the end of the center, which is exactly where we should be getting to. I might suggest, as you just did, that people send you questions via the chat or directly by email. That's probably the best way to deal with this. And given the time, we'll press straight on to the next speaker. So thanks again, Andrew.
Cheers.
So next up, we've got Dr. Arushi Manchanda from Tassie, who's going to talk about direct analysis of swab samples using thread-based analytical systems. Arushi, are you there?
Yes, I'm just sharing my screen.
Good. Oh, yeah, here we go. Okay.
So can you see my slides?
Yep, we'll live with that, I think. Yep.
So I'm going to talk about thread-based analysis of swabbed samples. So before that, what is thread-based electrofluidics? So thread-based electrofluidics is utilization of threads to construct fluidic channels to perform various analytical assays. And the advantages of using threads is that threads offer advantage over using paper as substrates, for microfluidic analytical devices because threads are more flexible, have higher mechanical strength, have a low cost and ease of functionalization. So, when we use thread for analytical devices, there are conventionally two ways of introducing sample on the threads. So either we apply direct application, and there is another way where we inject the sample in one of the reservoirs, and that is known as continuous injection. But now what we are looking into is direct injection from the swab. So swabs are basically swab-based sample collection is a widely used method for various analytical procedures because swabs have a tendency to collect samples from a variety of surfaces. But generally what happens is for analysis of swab samples, we take the swab and dissolve the sample in some solvent. So that dilutes the sample multiple folds and renders it unsuitable for rapid point of care analysis. But here what we are looking into is if we can get direct injection of sample from swab to the thread. So for that, we have developed a system. So here is an layout of our system. So we have introduced another well in addition to the two well conventional system. So as you can see, we here we have a swab with a fluorescent sample and which is in contact with the thread. So after we apply electric potential or current, what we see is complete transfer of solute from the swab to the thread, and the sample also concentrates into a small band. So we have further investigated this system for a variety of threads and a variety of swabs, and also we have used 3 analytes for now. Furthermore, we have also tried investigating the effect of matrices like saliva or cell lysing agent. So in this second well, we not just buffer, we also introduced some cell lysing agent or saliva, and we still see a transfer of material from the swab to the thread and concentration of the analyte on the thread. So for now, we have investigated only 2 matrices, cell lysing buffer and saliva. So the advantage of this system is that it can be used for direct analysis of biomolecules from cell. And furthermore, we are also investigating the potential use of this system in multiplexing. So where we can transfer a sample from a swab onto a single thread, and then if we can split that thread into multiple threads, we still if we split the thread, do we see the sample transferring from one thread to multiple threads? And yes, our initial investigation shows that we can transfer the material from one thread to multiple threads by just splitting them. And this method can be very useful for simultaneous analysis of one sample or a comprehensive analysis of a single sample. So up till now, we had been using different synthetic, natural, or organic threads such as cotton, nylon, polyester. But we have also started looking into using quartz or silica substrates for their use in thread-based electrofluidics. So the synthetic organic threads have disadvantages that they have irreproducible chemical and physical properties, and they do not allow for easy surface modifications because of their chemical susceptibility. And silica has been widely used in electrophoresis for a long time now. So we have 3 substrates here, which we have investigated: strand, strip, and twisted yarns. But these substrates are highly hydrophobic because of some coatings of anti-sizing agents. So because of these coatings, we could not see any electrophoretic movements initially. Then we went ahead and treated these substrates. We did plasma treatment to get rid of these hydrophobic coatings, and we confirmed that using FTIR that we can, if you look at these peaks after plasma treatment of 8 minutes, we do not see any band stretching due to hydrophobic coating. So yes, we can remove these hydrophobic coatings by plasma treatment. And after plasma treatment, we do see a good electrophoretic movement, at least on yarn and these strips. So if you all can see, this is a twisted silica yarn. And we do see electrophoretic movement of fluorescein, and then it further starts to concentrate into a thin band on this silica yarn. So yes, after plasma treatment, we have some initial results that we can have good electrophoretic movements on these silica substrates. And so we believe that these technologies have commercial importance in development of point-of-care and analytical devices, and in multiplexing, where we can analyze multiple samples, or we can do parallel analysis on same sample. With that, thank you, and I'll take any questions.
Okay, thank you. So, questions for Arushi? Maybe lead off if you can hear me all right. So do I gather from that that silica really is the way forward for you, silica fibers?
Yes, we're working on both the platforms, Swabbed-based as well as silica. And with silica, the advantage is if we can do on-thread fiber detection. So we are looking into if we can get there, and that would be like a step forward or a breakthrough in thread-based microfluidics.
Yeah, right. Okay, if there are no other questions, people can, of course, talk to Arushi on the chat box or email. In which case, we'll press on. Thank you for your good timing. And next up, we have Dr. Sepehr Talebian from Wollongong. He's going to talk about hydrogel structures for milk delivery.
Cool. So hi everyone, I'm Sepehr. Today I'll be presenting on the work that I've done during my PhD, which I finished in 2020. It was basically around application of coaxial hydrogel structures for drug delivery to tumors. So to give you a bit of background, there at the moment in the clinic, a lot of these drugs are administered systemically, which is then brought to certain shortcomings, such as you would need a large dose of these drugs initially. And then by the time this portion of this drug, a small portion of these drugs actually gets to the tumor, the drugs don't have enough bioavailability to get any therapeutic effect from them. And then lastly, because they're administered systemically, they have a poor biodistribution, and you get these negative side effects from these drugs, which is really bad because these drugs could be really expensive and it will jeopardize the health of the patients as well. So then on the other side, we have this concept of local drug delivery, which is basically you would use a drug delivery system and then implant that next to the tumor. By doing that, you basically diminish some of these negative side effects of these drugs that are associated with their systemic administration. So mainly, you would need smaller dose of the drug because then the implant would be implanted next to the tumor. And then these drugs will be subsequently protected from degradation because they're normally encapsulated in a gel or a polymer. You could actually impart certain spatiotemporal control over the release of these drugs. If it's a prolonged release, a shorter release, or a pulsatile in some cases. And then lastly, you can get a sustained therapeutic concentration over a longer period of time, which then helps with the ultimate therapeutic effect of these treatments. So along these lines, there have been different sort of implants that were used throughout time, whether it was more complex micro devices or less complex fibers or hydrogels that were injectable. Obviously, each had their own advantages and disadvantages, and they've been applied to different therapeutic methods, whether it was chemotherapeutic drugs or gene therapy or phototherapy, whatever the case might be. So basically, these implants give you a perfect platform to apply even multiple therapeutic approaches to these tumors, something that you can't really get with systemic administration of drugs. So along these lines, we next decided to use these coaxial wet spun fibers, but then we also included certain chemistries into the fibers. What we hypothesized was that if we use this molecule dopamine, which is a catechol, it would, and we attach it to this hydrogel alginate, then we would get these dopamine functionalized alginate, which would have some adhesive properties that can be used to give us some affinity towards these drugs that we have, aiming to prolong the release of these drugs. So we would have these dopamine functionalized alginate in the core of these fibers, and then to further slow down the release of these drugs, we would add a shell that is mainly made up of alginate methacrylate, which is basically UV cross-linkable alginate. And then we would get these coaxial fibers, which then later on can be either used individually or they can be weaved, or different textile manufacturing can be used to make these implants, which can ultimately be implanted next to the tumor. So then we make these fibers. Obviously, these are hydrogels we're talking about, and their swelling ratio is significantly high. So then we took microscopy images from the fibers in dry state, and in dry state, you don't see any porosity or nothing, but after they completely swell, you can clearly see the core and shell of these fibers and the different pore size distribution that is associated to the core or to the shell. So then what we've done next was that we focused on two specific chemotherapeutic drugs that are being used in clinic, one of them being gemcitabine and the other one being doxorubicin. And then we included these drugs into the core section of these fibers, and we measured the in vitro release profiles of these drugs. What we've also done was that we compared these to single fibers that were made from pure alginate, as well as core shell fibers, where both core and the shell were made up of alginate methacrylate, because we wanted to see the effect of dopamine modified alginate in the core. Anyway, after we've done these studies, for gemcitabine, we got a really short release profile, which is associated with the small molecular weight of the drug, as well as some functional groups on the molecule. But then what we observed was that the core shell fibers that we designed, they gave us the slowest release rate out of all these other formulation. And then when we looked at doxorubicin, we actually got a better result, because doxorubicin is generally larger molecules with more functional groups on it. And then with the core shell fibers, we were able to get a week of release from these fibers when we tested them in vitro. So these results were promising, and what we've done was that we've done in vitro studies on different pancreatic cancer cell lines in vitro. And what we've done was that we had gemcitabine, we either had gemcitabine in the fibers, or we had doxorubicin, or we also made fibers which included both of them simultaneously, calling them dual loading. So then what we observed was that when we used the dual treated fibers, basically dual loaded fibers, we got the best therapeutic efficacy in case of inhibiting the proliferation of these cancer cells in vitro over a period of 23 weeks, 21 days. And then when we moved on to in vivo studies, where we used subcutaneous pancreatic cancer tumors, and we implanted these fibers next to the tumor, we observed that similar results actually, where dual loaded fibers prohibited the proliferation of the tumor, the growth of the tumor, more than any other formulation that we've tried. And all these different fibers were tolerated in the animals. They didn't necessarily lose any weight. And then when we did the histology on the tumor tissues that were treated with different formulations, we observed, especially with Ki67 marker, which is a marker of growing and dividing cell, we observed that dual treated fiber had the least amount of dividing cells, which is then promising. What all we're trying to do is we're trying to slow down the growth of these tumors. And what we've also done was that we used equivalent dosage of the drugs that was in the fibers, and we systemically inject them to see what would be the difference between this local delivery and normal systemic delivery. And what we've observed was that the local delivery had significant reduction in tumor size when compared to the systemic injection of drugs, basically satisfied what we were trying to achieve. Then, based on the result that we've got, since doxorubicin was released in a prolonged manner, what we did next was that we used the same approach. Instead, this time in the shell section of these fibers, we used these copper selenide nanoparticles that have photothermal properties. Basically, when you shine a near-infrared laser to them, they generate heat. So then we made these core shell fibers, and we did the EDX mapping on them, and you can see the nanoparticles were only existing on the shell section of these fibers, which is what we designed previously. And then we've done in vitro, both in vitro and in vivo experiments where we shine them with near-infrared laser to see how the temperature will change. Basically, we used 2 centimeters of these fibers, and then when we did the in vivo subcutaneous models, you could see that they were able to raise the temperature up to 63, 64 Celsius. Then we've done some in vitro studies on these fibers using breast cancer cell lines, 41 breast cancer cell lines. Well, basically, it showed that after we did the simultaneous dual therapy with doxorubicin and with the nanoparticles, we got the most therapeutic efficacy. We also saw some negative effect of the core shell fibers alone by themselves. But then, interestingly enough, when we tested them on healthy fibroblast cells, we didn't see that effect. So we hypothesized that this could be associated with anti-cancer properties of dopamine molecule itself. We also done light staining of the cells, which then showed that the dual treated with doxorubicin and the laser basically killed all these breast cancer cells. We also done in vivo studies, and similar results were observed where dual therapy were capable of inhibiting the tumor growth. And then lastly, because we didn't get a good release results from those core shell fibers, especially in sense of gemcitabine, we decided to use the 3D printing facility that we have in ACES, especially the G-SEM printers. When we printed the same formulation, but we made some minor adjustments to adjust the release rate. So we still went with the core shell structures that we designed with the same formulation. Instead, what we've done was that we have used an additional cross-linker being calcium carbonate. So these patches either didn't have calcium carbonate, or they had the calcium carbonate, or after we made these patches with calcium carbonate, we subsequently coated them with PLA, which is a hydrophobic polymer, to further slow down the release of drugs. And then when we took the SEM images, you could see the effect of calcium carbonate in reducing the pore size diameter, and then eventually the PLA coating around these patches. So we've also done the swelling ratio studies to see how these modifications affected these patches. And after the final adjustment with calcium carbonate and PLA coating, we have significantly reduced swelling ratio, which is normally associated with burst release of the drugs. We've done the in vitro release studies on gemcitabine, and the samples that had both calcium carbonate and PLA, they showed a prolonged release of drugs up to 7 days. And interestingly enough, you could adjust the release rate by adjusting the number of these 3D printed layers, like we 3D printed 4 layers maximum. We tested them on pancreatic cancer cell line, and they were able to kill the pancreatic cell lines in vitro. And then we've done a prolonged study on in vitro prolonged studies on pancreatic cancer cell line MIA-PAPA2. And what we've observed was that the 4-layer structure, these are all with calcium carbonate and PLA coating, they were able to inhibit the cancer cell growth when compared to control samples that didn't have any drug in them. So then what we concluded was that this specific chemistry that we used, along with this coaxial design that we had in mind, it actually worked, whether you can make them with wet spinning technique or with more advanced 3D printing technologies. And we use them both for local chemotherapy and chemophotothermal therapy. And as I mentioned, we use the 3D printing to make these implantable patches. And then what's left to be done is more in vivo studies, especially on the 3D printed patches, as well as some in vivo studies on intrinsic and anti-cancer properties of these chemistries that we've chosen. So with that, I end my talk, and I'd like to thank everybody who helped me, Carl, Gordon, and everybody else, ACES, and I'll take your questions. Thank you.
All right, very good. Thank you, Sepehr. Questions? Sanjeev has one here. He says, what is the M/G ratio and molecular weight of the alginate you used?
I used the mid-average molecular weight alginate that was purchased from Sigma Aldrich. Off the top of my head, I'm not sure. I gotta look at my thesis.
Okay, very good.
I've got a question, just to comment maybe on the mechanical properties and the required mechanical properties for applications.
Yeah, so we did the mechanical properties as well. I didn't include them here in the slides given the time limits, but the coaxial structures compared to the single fibers, they significantly had improved mechanical properties. But then, yeah, you're right. That is an essential property, especially when you're implanting.
Okay, thank you. Another one from Jeff Spinks here. He says, how were the fibers implanted into or next to the tumor?
Oh, so the fibers were cut into small pieces, and we used the implantation needle, gauge 13, and we basically put these fibers next to the tumor. These are subcutaneous tumors.
That's a big question. How are you capping the ends though? Say you did cut it up. How do you know that it's not just flat?
Well, I mean, that is something that is associated with them. Obviously, when you're cutting them, you're exposing more surface area. It's gonna affect the release rate, but with the size of the tumors that we were able to induce in the animals, we didn't have any other option. But that is something that to be studied, really.
Right.
Did you look at the dissolvability at the time? So,
yeah.
So you're putting them in surgically, then I'm assuming that you're allowing the body to remove the substrate over time?
Okay, so we didn't necessarily look at the biodegradation rate of the implants, if that's what you had in mind, because at this point, we were just studying to see what would be the difference if we locally deliver the drugs compared to the systemic one. But then again, that is something that has to be done to make sure that the implant either completely degrades or if certain surgery is needed to take them out.
All right. Any last questions? And anybody in the audience, feel free to shout out. If not, thank you, Sepehr, once again.
Thank you.
Well done.
No worries.
And we'll move on to the next speaker, who's Holly Hunt, who's going to talk about hydrogel materials development. Thank you, Holly.
Does this work? Just switch on the side. No, maybe not. All right, we'll just be nice clicking. Oh, that's fine. All right, hello everybody. My name is Holly and I've been part of ACES for the last roughly 6 years. And I'm going to go through the various different projects which I worked on during that time. So it's going to be a little bit different. Rather than focusing on just one thing, I'm going to kind of touch between a few different things. Oh, Lauren, this isn't working. Okay, so my role within ACES was to develop functional hydrogel materials for various applications within the ACES teams. So as you'd imagine, each different team had very different requirements or intended applications, or sometimes particular materials that they want to use. So for example, synthetic biosystems want biocompatible, soft, and sometimes printable gels. Soft robotics usually want a tough, robust, but then also sometimes electrically conductive or responsive actuating gels. Electromaterials is much more simple from what I can see here. They just want electrically conductive gels, but usually also a lot of the other characteristics. And electrofluidics, we've developed some channeled or porous gels which could be used for their particular applications to meet their desired milestones. So to address the range of potential applications, as I mentioned, they vary greatly. So there's a lot of things that need to be considered. So, do you want to be softer or harder? How many materials do you want to get in there? What is each of those materials going to bring to the gel? And will they all work together? Will it be a matter of, like Sepehr was talking about, having different types of gels that are going to sit quite closely together, if it's a coaxial system or interpenetrating network? So a lot of things need to be considered when even going to get the materials to put together. Is it going to work from the inception? So I'm going to go through a few different techniques or materials or complex gels which I have developed. So the first one is using a pultrusion technique, which in industry is, if you sort of think of it as the opposite of extrusion, where instead of pushing stuff out, you are pulling a printing technique platform along some reinforcing fibers. So it's usually you'll use this to embed fibers within a plastic or material that you want to reinforce. But what I've done is then pulled those fibers out to leave hollow channels through the material. So I'll show you what I mean. This setup here is what I developed. And as you can see along the bottom, I'll try not to point too much because I know people can't see what I'm looking at. So these fibers are first threaded through this needle setup. So it can be anywhere from 5 to 16 fibers have been threaded through this. And then the hydrogel is pushed down and extruded out around those fibers while the whole setup is moving along a stage and being cross-linked as you go. So what you should get at the end looks something like this. Your hydrogel is extruded around in a continuous fashion, these long fibers that go all the way through the middle. And then we can remove them, and a cross section there at the bottom just shows the kind of end result. So you can get a nice channeled gel with these holes in it. You can then fill those holes with whatever you want or leave them hollow, depends on the application. You could have, electrical fibers, electrically conducting fibers stuck in there that you can stimulate your material directly, or you could use it to flow different liquids through the middle that are going to do something functional. So that was the very first thing I actually did during this fellowship. Now, another thing that we sort of came across as being useful was, rather than, when you make your polysaccharide hydrogels, usually you go and dump them in a cross-linking bath of salt. We found that, all you want to do is spit out divalent cations into these gels. So why not directly do that through oxidizing metal? So all this is, I know it looks a bit strange, but these are cross sections of gels that we made by growing them directly onto copper fibers. So by passing a current through the copper fiber, so the copper wire, you spit out ions, Cu2+ ions, which will cross-link the alginate bath that it's sitting in and slowly grow this gel around it. And it's really interesting because the closer you get to that copper wire, the harder the gel, and you get this complex system. Not really sure what you want to use it for, but we showed that you could make really complex grids of this stuff just by threading copper wire through, have a single anode, and then I was using a base cathode of aluminium foil, and it was growing these fantastic gels in a grid structure. It should just be noted as well that you can completely reversibly uncross-link these gels by reversing the bias of the voltage. So you can completely just turn them back into a gel-forming solution rather than a cross-linked gel. It could be used for drug release and various other applications. It does have some uses. So the next one, I touched base on that, saying that soft robotics often want mechanically robust hydrogels. So when you think of hydrogel materials, they're usually 99% water, 95% water, which doesn't make for the most strong materials. So you have to have a few techniques to make them stronger or more robust. So one such technique is ionic covalent entanglement networks. So here is an example of one which I use quite a bit. So alginate is your ionic network. NiPAM or poly-NiPAM is your covalently cross-link network. So they cross-link to themselves, but in an entangled fashion, which means that you get a gel which is both flexible and strong at the same time. And into that network, I also embedded carbon nanofibers, just to add difficulty to the whole preparation technique. And this created a really good gel. It's tough triple network ice hydrogel. And it ended up sitting, so that's a graph of fracture energy as a function of modulus. So it sat right up in the sort of rubber scale of things. So way above double network hydrogels and conventional hydrogels at the bottom there. That was really good. Now, because these gels, these ice gels, contained poly-NiPAM, as I said, for the covalent network, you can, poly-NiPAM is a gel which, when you heat up, it shrinks. And then when you cool it back down in the presence of water, it swells up again. So we're able to make these reversible actuating gels. And because there are carbon nanofibers in there, we're able to perform dual heating. So you didn't have to submerge it in a bath of hot water for it to do this. So all you need to do is plug in wires, pass a current through it, it dual heats, spits out water, and then shrinks right down. So you could think of this being used as, electronic valve, or in electrofluidic systems, you could, thermally heat these gels and allow liquid to flow once they shrink down, that kind of application. Now, based on what I was speaking about before with copper ions being used to cross-link polysaccharides, instead of just fully cross-linking the whole network and having it shrink, like that previous one I showed you, it was completely shrinking in every dimension, we can control that shrinkage by having just some parts of the gel cross-linked more than others. So let's show what I mean. So these schematics here sort of show where the copper electrodes are being placed on the gel. And if you tactically insert these regions of more hard material, when you go and actuate it, because there's poly-NiPAM in it, so when you put it into hot water, it will not just shrink in every direction, but it will fold in a complex pattern or shape. So again, not totally sure of the application of this, but it looks pretty cool, and I'm sure there will be some great people among us who can come up with a good application. Okay, so one of the issues when you look at these actuating hydrogels is based on the ability for water to get out of the bulk structure, because it has to go from right in the middle or wherever that interstitial water is to completely out of the whole thing. So if you have your usual hydrogel and you cross-linked it, if you look at the lovely cylinder I've drawn on the left, that water has to have a convoluted path to get out of the gel, and it takes quite a while. But if we can introduce these porous, empty pathways, all the water has to do is get to the closest one of those, and it has a free path right out of the hydrogel. So the reason for doing this is that hopefully we can speed up the actuation dramatically. And the other strange effect that we found when we were doing this is the very outside shell of the gel would be a lot kind of harder or drier. So if you don't have these pores in it, sometimes you'd see these bubbles forming just under the surface, and you just want the water to get out so it can function as a material, but it just wants to stay there as annoying little bubbles. So to do this, I had a removable shellac floss template. So all you need is to have a material that is not going to be soluble in water. So shellac is just one example. You can use any other materials that aren't soluble in water. So all you do is cast your hydrogel around this template, cross-link it, and then remove the template. So for this one, it was just removed by soaking in ethanol. But if you can think of other templates that you want to put in there that are dissolved in other ways, whatever you can think of, should be possible. So by doing this, I'm not sure if all of you can see the diagram, but that is volume of the gel over time. So how quickly it's shrinking. And you can see that without the channels, it's much slower to shrink compared to when there are channels in there. So suddenly it makes it much more useful as a soft robotic actuator. So if you have like a soft robotic hand and you're really slowly trying to grip something, it's probably not going to be all that exciting for someone you want to sell the hand to, but if you can actuate it much faster, it's going to be more applicable. Okay, and I think this is one of the last ones. I can't remember how many numbers I put in, but number 7, conductive hydrogels. So you can make conductive hydrogels using 2 different methods. One is electronically, by putting things such as carbon nanofibers, graphene, actual metal particles, whatever you're putting in there. Or you can simply go with salt. So ionic conductivity, we found, was actually 3 times or more than 3 times higher when it's in a wet gel. So something to keep your mind on when you're making your graphene hydrogels. It's sometimes easier just to chuck a bunch of salt in there. I did have another one. So biocompatible hydrogels. This is one of the ones I've been working on very recently. So making a wound healing patch, we have to make sure that the materials are all biocompatible, cell-friendly. In this case, it is made with ulvan methacrylate, which is bacteriostatic. So it's also not going to go nuts and grow a lot of bacteria. So cells grow on it happily. Bacteria doesn't grow on it very happily, so it's good. It's flexible and soft. It can conform to the body's particular shape. It can absorb liquid out of the wound, so that's what you want. You don't want a big soppy mess on your skin, and it's robust. So in this case, there is cotton gauze cast within it just to give it more handleability. So if you think of your typical hydrogels, your jelly, if you put that on your body and start moving around, it's probably going to break apart. So the cotton gauze just keeps it all together and makes it really good. So that was a big success. So in summary, we made a number of novel hydrogel, both systems and ways of preparing them. So they've been developed over the last few years. Each were characterized. I know I didn't put much data in here. You aren't all excited to see my data, but each of those was characterized in every way that was useful. And these systems work towards many of the ACES milestones. Again, I haven't put those in, but I assure you they were relevant. Now, I was trying to think of the list of people to thank, but there was far too many because I've worked with so many great people around here. So thank you all very much from the tea room conversations to helping me out in the lab to supervision to everything. So thank you all very much, and thanks for listening.
Thank you, Holly. Probably time for one question, if there is one.
Holly, I might jump in. Can I ask about your last biocompatible composite gel with cotton, and you were using for wound healing? Would the cells growing on have any implication to the wound healing process where you may find that your bandage could incorporate it within the wound?
Well, one of the things that we actually came up against when trying to seed the cells onto the bandage is they don't really want to stick very well.
Good.
So you really have to make them sit there. So I think it's going to be good for, when you go to remove the bandage, have the scab won't come with it.
Yeah.
Because that is a concern.
Yeah, but the cells growing on it means that it's not cytotoxic to the cell.
Exactly, yeah. So it's actually supporting the cell growth as well. The ulvan is giving out good nutrients and happy cells.
Thanks, Dan.
That's the technical term, right?
Holly, there's a quick question here from Sanjeev. He says, is there an effect of different bivalent ions on the stiffness of the hydrogel?
Yes, it's not really the divalent ion itself, it's more how densely packed they are. So I found that if you, let's say, insert a certain number of those divalent ions into the system and then remove the source of them, so in that case, the copper metal, you can then controllably move them through the gel by controlling the electric field. So I know it didn't really answer, but no, it doesn't matter what divalent ion you use, but yes, it does matter how densely packed they are. That will give you your different hardnesses and softnesses.
Yeah, good. All right, Holly, thank you very much. Very interesting. And we'll move on to Dr. Faezeh from Deakin, who will talk about development and use of novel Zwitterion-based electrolytes.
Hi, everyone. I just stop share and first. All right. Okay.
That's it. Yeah.
All right.
Okay.
So good afternoon, everyone. My name is Faezeh, and I'll be talking about advanced electrolytes for energy storage applications. We need to develop new electrolyte materials for beyond the lithium-ion battery technologies, like lithium metal batteries that can provide higher energy density, or sodium metal batteries that can provide cheaper batteries for some applications. To be able to use lithium metal or develop sodium metal batteries, we need to change the chemistry of the current lithium-ion batteries. For example, the electrolyte inside lithium-ion batteries are liquid electrolyte based on a mix of organic solvent electrolytes that are highly flammable. So they cause a lot of safety issues. And also they are not stable. It means that they will react with electrode materials, in particular with lithium and sodium metal that are highly reactive. And they can form the dendrite that can pass through the electrolyte and separator and lead to short circuit and catch fire. So in our group, we are tackling all this problem by developing new solid state electrolytes that are safe and also they are stable. One type of these electrolyte is organic ionic plastic crystals that are solid state family of ionic liquids that Christina talked about them yesterday. These materials are solid, but they are mechanically flexible solid because they go through some solid-solid phase transition at the solid state, and so they have disordered structure. And finally, at the highest temperature solid phase, just before melt, they are soft and plastic. So there have been a lot of progress in using using plastic crystals with different cations in combination with different anions in our group, in different devices like sodium device, lithium batteries, and also fuel cells. For example, we have used phosphonium cation plastic crystals with different alkyl chains in combination with different anion for sodium device applications. As an example here, we added a wide range of concentration of sodium salt into one type of phosphonium cation plastic crystal. And we have shown that the ionic conductivity of the whole concentration is very high. For example, at 50 degrees, all compositions have ionic conductivity higher than 10 to the power minus 4, which is high value for solid materials. So also, for example, here I showed you one high concentration of sodium salt that we measured in sodium symmetrical cell, and we observed the stripping and plating of sodium is very stable and very reversible in the sodium symmetrical cell. Then we wanted to know that really these plastic crystals can work in real sodium device or not. So then for the first time, we fabricated the sodium metal, sodium devices based on sodium metal anode and carbon-coated sodium vanadium phosphate cathode material in collaboration with Professor Linda Nazar at University of Waterloo in Canada, that her research group is expert in synthesizing cathode material for sodium devices. So we fabricated a sodium fuel cell based on one of our organic ionic plastic crystal mixed with sodium salt that we well characterized. And so we studied we did cyclic voltammetry of the fuel cell at two different temperatures, room temperature and at high temperature, 60 degrees. And we saw two redox peaks that is because of reversible transformation of vanadium 3 to vanadium 4. And interestingly, we saw that the potential interval between oxidation and reduction peak is less at higher temperature. That shows the lower polarization potential at higher temperature. And also the current density is clearly higher at higher temperature. So that shows the fast redox kinetic of the electrolyte. That's because the electrolyte has higher ionic conductivity at higher temperature at 60 degrees. And also we studied the rate capability of the cell, and we observed that the rate capability at both temperature is very well, but even better at higher temperature like 60 degrees. And for example, at fast charge and discharge rate, 15-minute charge, 15-minute discharge, we can get some capacity at 60 degrees. Which is excellent. And also the cell showed the stable long-term stability at high temperature, and in comparison with a commercial organic solvent electrolyte, that is the blue one here, this electrolyte has tendency to fail, and finally failed at around 60 cycles. So all these results showed that this plastic crystal in sodium devices, actually we can use this plastic crystal in sodium device, in particular at high temperature for some applications that need higher temperature. The mechanical integrity is also very important for the level of their performance. So we tried to combine the plastic crystal that I mentioned mixed with sodium salt. We combined them with the electrospoon PVDF support to make a freestanding composite electrolyte. So then we made this freestanding, self-standing composite electrolyte based on plastic crystal, phosphonium cation plastic crystal, and mixed with sodium salt, the sodium FSI that has the same anion as in a plastic crystal. And also we mix them with sodium TFSI that has different anion as in plastic crystal. So in this case, we have mixed anion. So we characterize them perfectly based on NMR characterization, thermal phase behavior, and ionic conductivity of them. And here is the cycling performance of these two composites, both of them in sodium symmetrical cell and sodium full cell showed excellent stability, long-term stability, but it is interesting that the composite based on mixed anion outperform the composite that has only FSI anion. That was based on our NMR characterization and thermal phase behavior. We found that that's because the interaction of TFSI anion with PVDF that make amorphous phase that has a higher ionic conductivity than crystalline phase that FSI system has. This work was published early this year. And so we filed a patent based on the results of application of plastic crystal in a sodium device. And also last year, we initiated 11 store with 3 other young researchers in our group. And we attended in a climate launchpad competition, which is promoting global green business ideas. And 11 store was successful in the Australian arena, and we won first prize in Southeast Asia. And also we eventually were successful in global grand final. And we won the Sustainability Mobility Theme Award. So the idea was to using sodium battery that is cheap and safe for scooter applications in Southeast Asia that the weather is high in that area. It's a hot weather, so the battery should be very safe and also cheap for those areas. So it was a big achievement. So the question is that, can we still improve the properties of plastic crystals in terms of having even higher target ion transfers number? When in the organic ionic plastic crystal, as I mentioned, when we add target ion into these materials, for example, lithium ion for lithium devices, we normally want only lithium ion to move through the electrolyte to do electrochemical reaction. But in the case of plastic crystal, all ions, including the ions in the matrix of plastic crystals, are also mobile. So we can improve the fraction of charge that is carried by only lithium ion. That is called the lithium transverse number. We can even improve this number in plastic crystal if we can suppress the mobility of cations and anions in the plastic crystal. So one possible way is tethering the cations and anions by bonding them covalently together. So in this case, we will have a molecule with net neutrality that won't move through the electrolyte. We call this brand new family of plastic crystal, Zwitterionic plastic crystals, that we expect that will lead to have higher target ion transfers number. So far, we reported 3 different Zwitterionic plastic crystals based on 3 fluoroborate anionic group and 3 different cationic group, which are pyrrolidinium, morpholonium, and pyridinium. And based on a variety of techniques, like combination of morphology studies, thermal phase behavior, and also NMR characterization, we found that there are a sufficient degree of disorder in the structure of these materials that can, like plastic crystal, can provide fast target ion conduction within the matrix of these plastic crystals. So we can use these materials as a matrix electrolyte and add target ion into them. So in this case, we, for example, as an example, I'm talking about pyrrolidinium one. So we added different concentration of lithium salt into the pyrrolidinium Zwitterion. And the ionic conductivity of the mixtures, all concentration is relatively high. And the interesting thing is that at low concentration and high concentration of lithium FSI, we have quasi-solid state electrolytes. And at the middle concentration, we have liquid electrolyte. And Lithium transfers measurement showed that the lithium transfers value is relatively high, and especially in at higher concentration of lithium salt, we have very high lithium transfers number. And also we measured the electrochemical stability of these materials, and the results showed that the materials is stable up to 5 volt. That means that we can use these materials with high voltage cathode material to have higher energy density and the higher capacity batteries. So based on all these results, we studied the electrochemical performance of the materials. As an example here, I'm talking about a low concentration lithium FSI that in this lithium symmetrical cell showed that the stripping and plating of lithium is very stable. And also we made a full cell in collaboration with Battery Hub, we made a full cell based on lithium metal anode and the LFP cathode, which is very stable and a safe cathode material for lithium batteries. And initially at the low C rate, we saw that the cycling performance is very stable. We are still working on these materials to improve the properties of, to improve the cycling performance of this plastic crystal, again in collaboration with Battery Hub. And also interestingly, it is very important that Coulombic efficiency is also very high in these materials. So all these results show that we can use Zwitterion, Zwitterionic plastic crystals in energy storage devices. So we recently filed a patent based on these results, and also we submitted a manuscript in the Nature Materials, and more manuscripts are under preparation. For the first time, we introduced a new brand family of plastic crystals that are exciting, promising, and novel class of materials, and called Zwitterionic plastic crystals. And as a future work, we will look at other types of Zwitterions, and we will work on them to use beyond lithium batteries. I would like to thank Professor Jenny Pringle, Associate Professor Luke Odell, Professor Mario Forsyth, Professor Patrick Howlett, and Professor Linda Nazar, and thank you for your attention.
Well done. Thank you very much. I think we've basically out of time now, Faezeh, so we'll say thank you, and excellent outcome with those patents, by the way, from your project.
Thank you.
Very good. So we'll move on to the last speaker of this section of the afternoon, who's Chong-Yong Lee from Wollongong, who's going to talk about perspective of electrolyte effects on electrochemical reduction of CO2. Take it away, Lee.
Thanks, Nat. Hi, good afternoon, everyone. So in the past 2 years, one of the focus of ACES is on the translations of including the CO2 reductions. So this talk is about what we learned, the experience we learned, and the perspective of how electrolyte actually can make the difference on the electrochemical reduction of CO2 and how actually impact the translation. So let me start with the motivation, which is why we spend our time and money on this, right? So I think that it's obvious that at the moment we talk about the increase in the CO2 level, and this has become headlines almost every year or every few months. And also CO2 level is increasing, and this correlates well with the increase in the temperature, which is about 1 compared with the pre-industry area. And if there is no control, and if it keep increasing for another 1 degree, then probably there's very bad consequences. And the impact actually not to us actually in our generation, but our next generation and generation after that, it's another 50 or 100 years. So, and that's why one of the ways actually we work in the lab is on to, instead of the CO2 released to the from the industry or the transportation released to the atmosphere, we capture it. We use electrochemical process to break the bonds and then create the new bonds. And this we do it through the renewable energy sources, and that produce the useful chemicals and fuels. So in order to do that, we need to use the CO2 electrolyzers, and there's a few components here on for the electrolyzer. The first one for sure is a catalyst, right? So this one is lower activation energy, then can operate at lower, higher currents and the lower potentials. And electrolyte is also an important part in this case, and it's an interface between the membrane and the catalyst, also depend on what type of electrolyte we use. And cell design particularly important if you want to know how we're going to introduce the CO2. So in this talk, I present on the electron aspect of how it influences translation. So let's look at what actually we need to have a benchmark. So benchmark for the CO2 electrolyzer is actually a solid oxide electrolysis. So in this case, we just have quite a regular product like carbon dioxide to carbon monoxide. So, and this is of course is a high temperature, but still a good benchmark. And they really get a very low slope here. So what's actually required here if a low cell voltage operate at a high current density? So what at the moment the low temperature electrolysis, what can achieve actually quite high voltage to achieve the reasonable good current density. But ideally we need, if the benchmark based on the water electrolyzer, we need about 500 milliamp. But that one we are above for 3 volt. So another one is we have to have a high current density because economically it is important for the capital cost. That means we have a fewer electrolyzer needed to achieve a required capacity for gas productions. So this is where we stand now. So I discussed one of the reasons because of electrolyte, one of the impact here. So we need to understand the chemistry of the interaction of the CO2 and in the water. Actually, it's not simple, and it's not like we use a water electrolyzer just pick the water. But in this case, there is a very strong pH dependent. So if we work in the alkaline solution, the challenge we are facing here is you convert to the carbonate here, CO2 2 minus. But if we work in between the neutral pH, so there is a combination between carbonate and also the bicarbonate. That means there is a carbon dioxide loss, which is not converted to the product, but instead become the ions. And if we work below the lower than pH 4, actually that's a good point, which we can use CO2 for the reduction. But there's a challenge here as well, which I'm going to explain. So if you look at the limitation and challenges, so the reduction part where the CO2 reduction happens. So in the near neutral actually is for industrial most not economics because it's low conductivity and low current density. If you want to compete with the assisted method, that's a challenge. But in alkaline electrolyte, it really show good high conductivity, high current density. It's actually ideal electrode, but we have a carbon dioxide loss as a carbonate ions. I'm going to show later the example of this, which we found, and also other research found as well. So if we use acidic, actually the most ideal, as I mentioned earlier, if we pH lower than 4, then we have actually ideal electrolyte that can have an existing carbon dioxide. But there's a strong hydrogen competition in this case. So of course the cell actually not only one part, the anode part is also important, right? And that is also actually contribute quite a large higher voltage as well. So in this case, like if we use water oxidation catalyst in alkaline, usually we need like 1.5 volt. So when you end up with the cathode for the higher, to get high current, it's always is above, usually it's in excess of 3 volt. And that again is limit the economics of the reactions. So I'm going to show 2 examples here on how actually electrolyte impact in this case the formate production, but in the case it can happen in other catalysts as well. So you can see from this curve, this work was performed by Ching Cho, a Gordon student she worked on this, investigate on the on the try to achieve the high current density and then using different electrolyte. But we found some challenges here. But firstly, you look at if you use KOH, is obviously is much conductive than for example, the potassium bicarbonate. It's about 5 times more conductive, and that's actually show the obvious advantage of why alkaline is better case. And but what we found actually the problems if you want to maintain the current stability, there's an issue with the interaction between the KOH and the carbon dioxide, so they form the potassium carbonate. So imagine you have 1 mole of CO2, and then you will react with 2 mole of the KOH, so you just have 50% left for the real CO2 to react. So there's a carbon, they call it the carbon loss in the reactions. So what we have to do actually to maintain the high currents, we have to use a high volume of the electrolyte. And that's the question now is the economics of reaction, whether it's economics, right? So, and of course, probably you ask, why not you just use, instead of 1 molar, why not use 2 or 3 molar? But we found it's not stable for this catalyst. So that's another challenge. So imagine if you want to do for long-term tanks or in the real application, we need to do for long-term. Like in this case, it's 30 hours. You can see we have to use a 1.5 liter of the KOH. So that means the use of KOH really, in principle, is not a really efficient way, although you can get a high current density. And of course, there's other factors to show that like the quality of gas diffusion layers, the catalyst product, but still fundamentally the electrolyte play a key role in this stability effect. Sorry. So, but there's one case of really, the real one case of using alkaline electrolyte, like the first thing you can see here, the suppression of hydrogen production is obvious. If you use, for example, 1 molar KOH, it's really suppress hydrogen production. And also you can suppress CO formation, and therefore all is quite a wide potential window across the range of the investigated potential. So if we compare the other electrolyte catalysts, this really have a real advantage in this full cell, and we can widen the potential windows, and also we can get a quite large current density. But of course, the carbon loss is one of the challenge. So another example I'm going to show here, this works actually I performed when I after a few months after I arrived at Wollongong. And Wollongong is a beachside city, so it's good to get some seawater, right? So there's many works actually studying using seawater for like the water splitting, but not really on the CO2. So this is just a curiosity for me at that point to understand what happens if we do this using seawater as an electrolyte for CO2 electrolysis. You can see here, if you use seawater from Wollongong, not Wollongong Beach, you can see it drop down the current. So what is the reason of that? So, and it shows actually the potential dependent. If let's say we use a low potential, it's not really negative cathodic potential, not really make a huge difference. But when you increase the potential, then the effect becomes more obvious. So we have to look at the seawater compositions here. You can see here there's not only how we have the sodium or chloride, we have many others cations and ions. So what we did actually to add in use cation and anion we have in the lab, and we put in the electrolyte, and we found that if we inject the calcium chloride, then you can see the drop in the current. If we 10 molar quite significant and 20 millimolar even more. So, and this confirmed to be the calcium carbonate formations. So that means if there's cation anions which is not inert with the CO2, there's potential of the reactions. So we have the two processes happening. First one is CO2 reductions to CO, in this case using a silver, and then also the competition of the proton reduction to hydrogen. And interestingly, we can actually capture the CO2 capture the CO2 in a carbonate form to form the calcium carbonate. So we have the reduction and the storage capture approach. So in conclusions, really we have to recognize there is a complex interaction between CO2 and water, and that's probably one of the key aspects we need to think about when you want to design the high performing electrolyzers. And at the moment, unlike water electrolysis, which electrolyzers where either acidic or alkaline is the best one. So far, there is no perfect electrolyte for CO2 electrolysis technology. And this actually offers the opportunity, many research opportunity to, for example, innovation in electrolyte, or either as an additive that actually can stabilize the system. Either if very acidic, how we can make the catalyst stable, or in alkalines, how actually we can prevent the carbonate formation. So there's many opportunity ahead, I think, in these areas, and how we can use electrolyte to make it more selective and also make it more efficient. So I'd like to thank especially Jingzhou and Gordon on this work, and also others which have direct or indirect contributions and help us support throughout these years when I'm working on this CO2 electrolysis technology. And finally, I would like to thank you for your attention, and hope we can do something to actually make a greener planet, reduce the CO2. Thank you.
Well done, Lee. Very interesting indeed. Got just a minute or two for questions here. All right, I'll dive in with one that's on my mind. The observation of I think you said it was the calcium carbonate you thought was precipitating in the seawater case. Is that right?
Yeah.
Yeah. Was that a flowing system, or is it static electrolyte that you studied there?
The one I show here is the static, but I'm working on the flow system as well, flow cell system as well.
Is there a potential that flowing quite rapidly a lot of seawater, that may be impractical in other ways, but nonetheless, might it fix that problem of sweeping out the calcium and the carbonate before it can precipitate? Well, carbonate.
You mean to prevent the precipitation of calcium carbonate?
Yes.
Well, the flow
yeah, exactly. Flow away the precipitation. That's different true. That's what we found. That's different true.
Yeah. Okay, good. Thank you. Any other questions? All right.
So I've got just on the seawater again. So where does the pH fall on the seawater and the complication of that with your electrolyte and the products?
Yeah, seawater actually usually at a pH about 8, around 8. And if we purge CO2, that will be a bit more acidic. But still, in the localized area, will be more alkaline. Even if it's very acidic, let's say very strong acids, in the localized area, you would eventually become alkaline.
So you're going to battle that challenge as well.
In seawater, it's okay because it's the most neutral. Yeah.
Okay. All right. Good stuff.